Remember that is the interesting case in which we can combine separation, molecular separation, and chemical reaction. And we are not on large industrial scale application yet, but people involved in research are all working on a possibility to realize more and more this kind of system, starting from the preparation of a catalytic membrane reactor. That means starting from system in which you can combine catalyst with the membrane function. And we saw last time that we can have membranes in which the catalyst is just entrapped in the membrane itself, or system in which the membrane operation is combined with traditional chemical reactors. And in one case is external reactor, in external membrane reactors, the other case just intrinsic catalytic membrane system. And the various properties of the system are very much related to what we have been already describing in the single membrane units combined with the typical parameters and phenomena which characterize any chemical conversion. The general relationship that we have between the transmembrane flux, that is the parameter we measure more normally, is the one that we have been discussing many times, in which we have a proportionality of the flux with the driving force. There is one term that we have not been using too much until now, but it's better you learn how to use, because there is a difference between what is called permeability and permeance. And this difference can sometimes origin some confusion in the data from the literature. When you are transferred, you find some data, especially in gas separation, and you transfer to your data, and if you don't find good agreement, be careful to be sure that if you are talking about permeance or permeability. And the difference is membrane thickness. So in general, when you don't know membrane thickness, you have a permeance. And if you know the membrane thickness, you have this permeability. But in this case, the difference in there are different dimensions between the two parameters. So be always careful. There is no, they are not the same. The kind of relationship is the same. It's a term of proportionality between transmembrane flux and driving force. But the dimension of the permeance and permeability are different. Numerical value can be different. So don't use the same same numbers if we don't understand what you're talking about. And all the difference is basically here. As we know already, this permeability or permeance, in this case exactly the same concept, is very much related to the chemical nature of your membranes. Can be metal, can be ceramic, can be polymeric, and the morphology, the overall structure. That means they can be dense, they can be porous, which means that we have to consider the different properties of the membranes as related to not only to the intrinsic property of the material forming the membranes or the catalyst that are just combined with the membranes, but also we have to understand in which configuration we are using our membranes, and that makes significant difference. Just to show you when we were talking about permeability and permeance, you can see here that the dimensions are different. This is square m, and that is just m. Just because in one case we have this thickness, in the other case we don't have. So that means are two different parameters, and they can have to be utilized in the right way. The driving force that is just moving our species across the system is something that we know already, and depending from the morphology of our membranes, we will have different kind of values for the term of proportionality. The driving force depends from the transport mechanism, that we can have a Knudsen diffusion if the membrane is a porous one, And the Knudsen diffusion, we know, we discussed already, which is kind of the relationship that characterizing the Knudsen diffusion coefficients, we will see. But the expression, the driving force, the function of the, it can be normally also in all these cases, is just assuming that is different pressure, but cannot be pressure. That can be the same relationship, can be in general to delta T, delta C, or something different. Normally, most part of the operation we've been discussing until now is we are talking mainly of a pressure driver membrane operation, and that's why we are always using as the driving force delta P, but can be also something different. And this delta P is a proportion, that is the term that we are going to use for each one of our parameters. So I was mentioning, depending from the kind of morphology, we can have different kind of mechanisms, and we are familiar with them. For example, we can have just viscous flow. Viscous flow, you remember when there's the size of the pore is relatively large, and there is this interaction between the particle. It can be significant. We have this typical Hagen-Poiseuille expression in which the transmembrane flux is related to the overall porosity, to the reverse to the viscosity of the medium. That is, this term tau is this tortuosity of the porous system, and there is the size of the pore, the thickness of the membrane, and the driving force. So all these term here is what we normally assume is a constant of proportionality, and delta P is the our driving force. Pore of the size of the pore, viscosity, tortuosity. One term which is very important, remember that in this situation we have to measure what is the surface porosity. This term epsilon, that means not 100% of the surface is open for the transfer of the chemicals. So we have to know really which percent of the surface is characterized by the presence of a pore. This is the part that we are interested. It makes a big difference if we have a lot of pore, small eventually, or if you have one single pore very large. That can be apparently, we can have the same surface porosity, but a totally different kind of mechanism. So the surface porosity is a term that we have to understand and to use, and it's just defined as this number of the pore multiplied for the surface of the pore divided for the overall, for the total surface of your membrane. The geometric surface is this A here. This one is just the single pore multiplied for the number of pore and the membrane area, basically. So that's something that we have to know. We can have a different behavior when the size of the pore is relatively smaller than the one of the viscous one, and you can see here that the major difference, remember that in the viscous flow we have a flux which is proportional to the delta P, and when you're talking about, and there's no molecular weight involved in the expression, in the Knudsen flow we have the overall flux is proportional to the driving force, so there is always a linear relation, but that you see here that in this term what we have is this reverse of the square root of the molecular weight of the penetrant, of the molecules that are going through. So the diffusion, the Knudsen diffusion coefficient, this delta is proportional, is given by this kind of expression, where we have the temperature, absolute temperature, the molecular weight of the species, and the number of the pore. Molecular weight means that depending from the molecular weight of the chemicals, if this is true, these smaller molecules, they will go faster, and the bigger molecule will go slower, and that we can separate. As we discussed already a little bit when we were talking about gas separation, that we can use this kind of expression to separate uranium, the isotopes, uranium-235 from 238, depending just by the ratio of the molecular weight reverse of the single molecules. The overall, if you want to check the behavior of your flux as function of the temperature, that's a typical expression that we can use, and that's basically is this activated phenomena in which we have again our flux proportional to the driving force, but in terms of if we change the temperature, this is the term we have to assume, which is a typical Arrhenius behavior. It means a statistical Boltzmann behavior in the system, and that depending from the temperature, we can just change. And this is exponential of this activation energy for R, that is a constant, universal constant of gases for the absolute temperature and delta. So that is the typical expression, and this is, by the way, the morphology of most part of the membranes that we are using. This is valid for the traditional porous membranes, viscous flow, porous flow. Remember that we discussed last time that we can also have some other kind of behaviors that make this kind of equation not 100% valid. We can have a surface diffusion, we can have a capillary condensation, and we can have the overlapping at the transit between Knudsen and viscous. So sometimes these things are not so easy, not easy to define viscous or Knudsen, because there can be overlapping or some other form of some other phenomena, adsorption on the wall, surface on the wall, diffusion on the wall, etc., which makes things a little bit more complicated. A totally different kind of system, which is very similar to the one that we have been discussing as a dense membranes, is the case, for example, of the palladium-based membranes. We have been discussing this because this is an interesting case in which we have a lot of industrial membranes available. And in many reactors in which people are working, this kind of membranes is utilized today, and in future maybe some other kind of metal membranes can be also utilized. That is particularly true if you are talking about hydrogen. Hydrogen production and purification using membranes in fuel cell, etc., for the problem of CO that we will see is a typical, is done normally using palladium. And the motivation for this interest in this kind of application is here, that basically palladium has the capability to leave only hydrogen going through. No oxygen, no nitrogen, no metals of any other kind that can go through. And just this hydrogen just can be dissolved and permeate 100%. So it's kind of mechanism very similar to solubility, diffusivity, the same kind of mechanism that we are using we discuss in reverse osmosis and similar, but with some special properties that you can see here. What is really happening in a palladium system, and that can be extrapolated to some other system, that's why people are still trying to understand more the mechanism. This is not 100% accepted, but is the most accepted vision. You can see here, gases, except inert gas, but gases normally don't exist as a single atoms. They only exist as molecules from two atoms, at least that is true for oxygen, for hydrogen, etc. Some other few gases are just single, but not the most common: nitrogen, oxygen, hydrogen, etc. So what is happening here? That we normally have these molecules of hydrogen, but there is what is called one kind of phenomenon that is called dissociative adsorption. When the hydrogen is interacting, arriving on the membrane surface, what is going through is not H2, but you have a dissociation of these molecules and forming single hydrogen. What is really going through the membranes is not H2, is H. But H is very unstable. It's stable only when it's dissociated and start to move across your palladium. Otherwise, does not exist in this form. Keep in mind, this is a quite interesting and complicated story, because if anybody of you in the future is interested in what is called the cold fusion, you probably heard something about cold fusion, the possibility to produce energy by transfer of hydrogen in palladium, by the way. And there were people trying to grow a new form of energy just doing this way. This kind of phenomena has some relationship to the cold fusion. but we cannot discuss about this. But if you do this, so you have first step, dissociative adsorption. After you have a solution diffusion mechanism through the dense palladium membrane that we are considering, and desorption on the other face of your membrane, and molecular association. So apparently nothing happened because you are just supplying hydrogen as a molecules with two atoms, and you produce hydrogen as a form of molecule with two atoms. So apparently everything is simple, but it's not so simple. If you want to predict the permeability and the selectivity, etc., there's no way you can understand what is happening if you assume that just H2 is going through. If you assume that you just dissociate and reassociate, etc., that's the mechanism that you can use it. Okay? So that's why that is the system that you have to consider. And if this is the system, what is happening here is that you have in principle, for what we are more interested, this solubility diffusivity mechanism, very familiar to you because it's the one we've been discussing already for in liquid, reverse osmosis, and in the gas separation. There's a special equation that experimentally has been tested. That means the driving force depends on the what is called the sievert permeation, just in the palladium-based membranes. The sievert permeation is telling you that this flux across your membrane is proportional to the square root of the pressure of the system. So you have this kind of relationship in which this driving force is equal to the square root of the partial pressure of the species I on the reaction side minus the square root of the pressure of the same species on the permeate side. This is called the sievert permeation, and is the one that can explain this mechanism we were showing before. Basically, that is the equation that you have to consider, that the transmembrane flux for hydrogen is proportional to the sievert permeability multiplied for this exponential of the activation energy divided RNT, divided for the thickness of our membranes, and multiplied for the driving force, in this case the sievert driving force, in nothing more than the square root of the hydrogen on the feed side minus the square root of the hydrogen on the permeate side. Okay? And if you just use this kind of equation, you can just well describe the permeability in different kind of situation, which is just related to the kind of expression. And for what concerns the dependence from the temperature, is typical Arrhenius law, and that is what you see here. That is the permeability as function of temperature, and we have a typical activated behavior that is the one that is described by this kind of expression. This does not work. Thickness of the membrane can also have significant influence in this kind of operation. You can see here that is the case in which we are working with 10 microns palladium-based membranes. The sievert flux across is of the order, you can see the number here, 0.48 in this in the units we are using here, and changing the pressure in the abscissa here is just functional temperature. Changing the pressure, you can have a significant increasing of this sievert flux at 10 microns. And if you just, on the permeate side here, we always have the same driving force, because the permeate side we are assuming 1 bar, and this is the, on the retentate side, 30 bar, 20, 10, 5, 2. But if I change the thickness of my membranes, the system is no more 4, but you see here at 50 microns, everything is 1 order lower in your transmembrane flux, as expected from the equation we were showing before, and there's 1.6082 as function of temperature. But for the rest, the behavior is exactly the one that is well expressed by the equation we have been showing before. So, but the thickness of our palladium membranes has to be quite well considered. Remember that we were mentioning that normally in a lot of study, people are defining the properties of permeation in the gas separation system without considering too much the kind of phenomena that we have been describing with attention, spending some time in the liquid phase, and that we call concentration polarization, fouling, etc. And remember that fouling and concentration polarization are not the same, but they are interrelated. If you have a lot of high concentration polarization, you can induce easy form of fouling. But two phenomena are totally different. In gas, normally, related to the high diffusivity, for example, of the gases compared to the liquids, the problem of concentration polarization, that means the growing of a concentration profile on the feed side of your membranes, and eventually also on the downstream, your membrane was not very, very visible and not very important, except when you have a special kind of gas, etc. We know today that the interface phenomena have to be considered with much more attention than one time. And for example, just the case of hydrogen, that is true for any kind of membrane, is true for polymers, but is true also particularly for palladium, where people today, palladium has been well utilized in membrane. Palladium normally utilized in fuel cell, where we have the problem of CO, CO2, etc. That's why there were misunderstanding, not understanding of the experimental results, etc. So people have to spend time, we had to spend time to try to understand better what was going on. And today you will see in the literature, if you are more interested, a lot of work trying to introduce the interfacial phenomena, poisoning, inhibition phenomena, concentration polarization to explain the real result that we have in the fuel cell when you are working in fuel cell. First of all, just to remember that when you are talking about concentration polarization, this P stands for polarization, is nothing more than this is our membranes, and normally you have homogeneous solution on the feed side, and that means the concentration is the same in any small elements that you are trying to characterize. But as soon as you start to permeate something, situation is changing. What is happening here is that if the membrane that we have here is semi-permeable, something is going through the species that are permeable in the membrane. The ones that are not permeable, they will start to concentrate at the interface. When they concentrate, you create a back diffusion. You create just a difference of the concentration at the interface and the concentration in the bulk for each species. So in principle, you have back diffusion. However, the value, the flux, the convection to the membrane surface is always much more significant than the back diffusion. In liquid, big problem. In gases, this back diffusion, this coefficient is much higher than in liquid, so this phenomenon can be a little bit less severe because back diffusion, the convection is on the membrane surface. The back diffusion is removing from the... So if these two fluxes are equal, there is no problem, but they are not equal. This one is much higher than this one, and that's why in the relatively very short period of time, you can have that the concentration in the bulk is no more equal and uniform all along this, all the feed side, but we start to increase, and we arrive to a concentration at the interface that is the real membrane concentration. And all the other phenomena following, permeability, etc., are related not to this concentration, but to this one. This is the one that's controlling this osmotic pressure, if we have any osmotic phenomena, not in gas phase, but in solution. This is the kind of concentration that can create, eventually, induce the formation of additional resistance formation of a gel layer, if there is something that can gelify, etc., etc. So that is the kind of phenomena, and if you want to know more about this and you want to calculate the concentration of the interface, what we have to do is to write down this equation, this differential equation, put in the appropriate boundary condition and try to integrate. The integration can be a little bit complicated if we assume that the concentration is changing, etc. So you have the film theory, assume that here is not linear, but all this kind of behavior is becoming a linear behavior, so the integration is much easier between, and everything is uniform in this stagnation layer, in the boundary layer. So we have to integrate between Chem and C bulk, basically, and there is a difference in this interval, so you have this convective flux, back diffusion, equal to what is going across your membranes. So that's the differential equation that is coming from this film theory, and that's exactly the same equation that we can use in reverse osmosis, in ultrafiltration, and in the palladium membrane that we are discussing. So that is the kind of problem. So we have an accumulation of non-permeating species in correspondence to the membrane surface, which change this separation performance of the membranes. Okay, so that was something that we have to consider. This problem can be a little bit more complicated, and first of all, if you want just to see what does means in terms of calculation, in terms of changing of the driving force, basically, this is typical situation that we have if there is no concentration polarization, where we will have a certain pressure and the partial pressure of our component on the feed side, a certain concentration on the permeate side, and that is the difference between the feed and the permeate, and that is the driving force. And that's because that is just the difference in concentration. What is happening if we have a concentration polarization is that this concentration here, this pressure is not this one, but is going down here. And that is on the other side, this one. So that the real driving force will be no more this one, but will be this one. Because just we have this change of the different value of the concentration on one side and on the other side. So just a decreasing of the driving force in our system. That's the same kind of expression. That means what we have to introduce, we can introduce a concentration polarization coefficients, and the concentration polarization coefficients is nothing more than the delta of the square of remember that we are using the Sievert equation, this pressure of the hydrogen on the membrane side, divide on the one in the bulk, and that's the membrane feed, bulk feed, membrane permeate, bulk permeate on both sides, and there is a difference between the value at the membrane interface, upstream and downstream. So you have to consider this difference, and that will be the concentration polarization coefficient that we have to introduce and to correct the driving force that is minor than the one we had before. So now we will have here this transmembrane flux that is proportional to the permeance to this term here, where we have to consider this coefficient given by this ratio and this square root, as a Sievert was showing, of the partial pressure of the penetrance. That is valid, all this discussion is valid independently from any chemical reaction. And it's the same kind of discussion that we have been doing in the gas separation, not a little bit different if you are considering this palladium story, but exactly the same story. Now we are considering that we can have also a chemical reaction in the system. So if you have a chemical reaction, in our mass balance, we have to consider also the term of accumulation. Something is going to be produced. So we have to consider that the accumulation, for example, of hydrogen, we are producing hydrogen, will be equal of the hydrogen which is coming in minus the hydrogen that is coming out plus the hydrogen we are producing. So that is the little bit the difference when we are considering chemical reactors. So now we have to, if you are going back to our membrane reactors, based on a palladium alloys, all the membranes, what I told until now to you was wrong. We never use palladium membranes. Palladium membrane cannot be utilized because when hydrogen start to penetrate in the structure of palladium, the palladium is becoming very brittle. And so very quickly you just break and you destroy. The way to solve the problem is not working with palladium, but working with palladium alloys, which means palladium plus some percent of metals, can be nickel, can be vanadium, etc. Still today, silver, normally is a silver, a typical good palladium alloys. So you are working normally with palladium alloys, and we have to rewrite our equation in which we have the term of accumulation, and will be given by this hydrogen entering, the hydrogen going out. This is part is leaving the membranes and part is permeating through our membranes, and the hydrogen we are producing. The term of production is the one that we have to now to introduce and to learn. That is, by the way, this is the expression that we are considering on the reaction side, and that is we have to write something as exactly the same kind of mass balance on the permeation side. So that's for the reaction side. On the depermeation side, we have exactly that we will have an accumulation on the permeate side, in which there will be some hydrogen arriving through the membranes, basically, and there will be the hydrogen which permeate through the membrane and hydrogen that is leaving the system. So you have hydrogen in, hydrogen out, and that is the term of accumulation that we will have. Normally, in a lot of situations, on the permeate side, we don't have reactions. So basically, this term here, the production side, is negligible, is not considered. And the accumulation term of the reaction and permeate side are also zero when you are in a steady state. What is when there is equilibrium, what is formed is also destroyed. So basically, you are zero term. How we can realize this kind of system? Again, I told you these are not easy system, and you can have different form of membrane reactors. And the typical case are also different depending for single geometry. This is typical case for tubular membranes reactors, and we saw some of these flow sheet already. But also for a tubular reactor, we can have at least 3 different membrane reactors. And we have to consider 3 different kind of operation. And that change the value of the driving force and the final the performance. We can have a typical tubular system in which we have the feed, and we pressurize on one side, and we can have a permeation of hydrogen across our membrane. So we will have feed, and what we call, for example, plug flow, just apply the pressure on the normal to the membrane surface. We will have a retentate and we will have a permeate. But that is that's for if you want to study these things. You are not supposed to study all this system in this course, but you have to know that these things exist, and if tomorrow you will have to study or to understand this kind of system, you have to know that you have plug flow membrane reactors where we have one-dimensional first-order model. You can have a system in which you have to consider also the axial diffusion along the tube, and that can be just a component that is not just the plug flow, but the axial diffusion that will be one-dimensional second-order model. And you can have both axial diffusion but also radial diffusion. So you can have different value of the concentration, changing the distance from the membrane surface. So you can have, in this case, axial and radial diffusion, second order model and 2-dimensional, one-dimensional second order and one-dimensional first order. So all this kind of system has been studied, and has been also that you can find a lot of this data in the literature, and this is some of the way in which this system can operate. You can have the tube-in-tube, as the one I was showing before, as annular membrane reactors. In this case, you can see that you can pack your catalyst outside the central tubes, and this is in between the vessel, the external vessel, and the tube, which is permeable. So that is the palladium membranes. You can have, in this case, a sweep gas inside this tube that will remove the permeate, the hydrogen that is going through, and you have the feed, which is just outside in the catalytic bed, basically. Here the reaction takes place, and the hydrogen is going across your system. And one of the three models I was showing before can well describe what is happening here. So we can have, in this case, an annular membrane reactor with the catalyst packed in the annular space. You can have another way of doing, in which the catalyst, instead of being compartmentalized between the vessel and the tubular membranes inside, is just can be just the membrane itself. The membrane itself can be just the catalyst, or the catalyst can be just inside, the catalyst in this case, forget the membrane itself, the catalyst is just inside the tube. So basically the feed is not going from in the annular system between vessel and the tube. The feed that was entering here, now the feed is just entering in this palladium membranes. The feed is inside. In the feed, in the inside of the tube is your catalyst. The reaction is taking place here. The hydrogen, in this case, is going outside. From this is going out, and you can just permeate from this compartment between the tube and the vessel of your system. So just the opposite, two different kind of situation. Which one is better? It's not very so easy, obvious how to predict these things, because it's a question of the recovery factor, the permeation you have, eventually of the temperature which you are working, etc., etc. And if you want to make your mass balance in this kind of tubular reactors, you can write the mass balance on the reaction side, on the permeate side, and you will have the overall permeation of the hydrogen across your membranes, which is the expression we just wrote before, where you have that is the flux of the hydrogen is proportional to the permeability coefficient, the term, the Arrhenius expression for what concerns temperature, and the delta P sievert form divided by the palladium, by the thickness of your membranes, basically. That's on these, in the case in which you have hydrogen going through. If there is no hydrogen, that there is this term will be zero, basically. There is no flux across your membranes. But that is the typical expression that we already assigned before. In batch membrane reactors, that is the situation, where, as I mentioned, this is a little bit easier when you just have transport to the membrane surface, normal to the membrane surface. So you can just write down for the batch membrane reactor, on the reaction side, on the permeate side, the expression for the term, the delta P, the reaction on delta T, on will be equal to the product of this membrane surface, reaction volume, flux of the permeation species, and that is the term in which you have this value, the reaction velocity for single components in the reaction volume. And that's it. You can write on the reaction side, and you can write on the permeation side. As I was mentioning before, don't worry too much about this, because we will not assume that you are expert in chemical reaction, so you will not have to integrate, but just to know how is the situation, what is changing. If you have not a batch system as the one before, but you have a continuous stirrer tank membrane reactor, as this one, in which the difference is that in the previous form, to make clear, we have no separation, just what is entering is going through the membranes and there is no other recirculation. In this case here, we have on the feed that is entering the system and something is going through and we will remove continuously and the retentate will be removed also. So we have a cross flow here and in principle we have a sweep gas downstream our membrane that will remove the permeate side. So totally different from what we wrote before, in which the species will accumulate and they are not removed from the system. If you want to write, in this case, the continuous stirred-tank membrane reactors, the equation will be exactly the same, but we have to consider the term, the sweep gas term that will be here, and the sweep gas term that will just giving you on the permeate side the continuous removal of the hydrogen that is going through your membranes. And that is just the major difference between the previous equation and the equation that we have to consider in this case. If you want eventually become more sophisticated and you have to analyze the system in its complexity and you want to check everything what happens in terms of heat transport, the energy transport in the system, the way to find a solution, to describe, to model the solution, is to consider a series of thermal resistance. That is the one that you can consider. You have all your reactors in this, assuming that is this is the reactor axis, and this is the anode side, and everything is the furnace. That means where you create your temperature, and assuming all these resistance in series, and that you can just write for each term, for the polar support, for the tube side, for the anode side, etc., the different equation, and trying to solve the system. Not very easy. That's something you must be some expert, but can be done. Basically, you can have a system in which you have heat exchange between reaction volume and the system supplying the energy at temperature. That means a furnace. Normally your reactor will be in a heating system, and you can have isothermal membrane reactors, you can have annular membrane reactor with high heat flux basically, tubular membrane reactor with relatively low heat flux, and adiabatic membrane reactor with no exchange of temperature between the system. And each one of these will be characterized by this heat transfer across the membranes and with this our system. That is something that we are not considering at the moment, but you can just write the equation as we made before on the annulus, on the tube side, and you will see, you will have the same kind of system. And at the end, you can have energy balance equation in which you can have to consider what is interesting, the heat generated by chemical reaction. Chemical reaction, as you know, can produce energy or can absorb energy. So you have to consider this change in temperature, that means change in the heat generated on the reaction side and on the permeate side, and the enthalpy flux associated to hydrogen permeation. And that's something that is present in the permeate, not on the concentrate side. What is interesting, that if you are able to handle this kind of heat balance, of energy balance, and the chemical transformation, and you now trying to apply the results of this kind of analysis to your system, you have some interesting results. Some of them, in principle, unexpected, expected when you know the problem, but unexpected before. For example, if you look at this reaction is a typical reaction that we are discussing, where CO is going to what is called the water-gas shift. Water-gas shift reaction is quite important because it's the reaction for which the CO is transformed, reacting with water, is forming CO2 and hydrogen. So this is the reaction that we are using upstream fuel cell to reduce these poisoning compounds coming from the steam reforming, where we are forming also hydrogen, but together with hydrogen in steam reforming, we form CO. This CO is poisoning the electrodes that we are using fuel cell, so as to be eliminated down less. What is accepted is less than 10 ppm, nothing. This reaction well, you see there's no change in the number of mole. The number of mole is this on the reactant and on the product is equal. So you don't expect any change, any influence on the pressure on this, in terms of clauses of the basic equation mass balance in any chemical reaction. You don't expect any influence related to the pressure because there is no change in the number of mole. Now, if you just make your experiment and you plot this CO converted as functional temperature, for example, the traditional reactor is giving you this kind of result here. But if you're now looking at what happened on the membrane reactors, you can have a similar behavior, much better interesting, because you are removing continuously one of the product. The hydrogen is going through your membranes, so that means the system is becoming more interesting. But what is also interesting, that if you change the pressure from 1 bar, the same down here, you go to 5 bar, 10 bar, you will see that the CO conversion increase with the sweep factor. So if you have a difference in pressure across your membranes that you can realize, for example, with having a sweep factor, we can improve still the productivity of the system applying pressure. That the Le Chatelier principle, the basic equation that characterize any chemical conversion, was not suggesting. So if when you pass your examination in chemistry, the Le Chatelier is one of the equations you're supposed to know, otherwise you don't pass the examination in chemistry. And this, Le Chatelier is telling you, which is a principle, by the way, is telling you that for this kind of reaction, pressure has no effect. If you are in a membrane system, there is an effect, because when you apply the pressure, you are never approaching the Le Chatelier conclusion, because you are continuously removing one of the product of the reaction. You are continuously moving your membranes across, and so that's why you have to consider that another situation, very different from the traditional one, positive, because you can improve the CO conversion just changing also the pressure. You can define this sweep factor, which is nothing more than sweep flow rate divided the feed flow rate, which is that is just creating the situation. This is one of the first example of interest of the conclusion. This is the reaction, the same kind of another case in which is the steam reforming, the reaction upstream, the water gas shift. In this case, you have a change in the number of mole. This delta N is equal to, basically. And you can see here now again the methane conversion as function of temperature, also in this case, but this was very expected case because you have the variation. And the traditional reactors is also affected. And if you are working at 10 bar or 5 bar, you have a different behavior. But in this case, or if you're working 1 bar, but in the case of when we are working as expected, there is delta N is 2, and these are 2 and 1 3 mole. Here is 4 and 1 5. So you are decreasing the number of the mole, total mole. That's why the effect of pressure is on the other direction. You are just decreasing the conversion, and the same is in the case of the membrane reactors. Again, you have 1, 5 or 5, 10, you have an increasing of the performance of the system. So that is one benefit. Not only you can make reversible irreversible, not only you can improve in terms of footprint, etc., but you can also have an interesting effect. You can use the pressure and playing with the permeability across your membranes, you can have an increasing of the conversion of your production of hydrogen and the conversion of methane in the steam reforming. And that's another case in which this reaction is very well studied, and in perspective is one of the reactions that is, if you go in the literature, you will see that everybody interested in this field is looking to the system, including trying to make perovskite membranes, etc., because that is one of the ways in which we can have a lot of benefits if we optimize this kind of system. By the way, all this discussion has been done on typical inorganic reaction, high temperature, by the way. These are all reactions relatively high temperature, and these are the first one people have been studying and using just because the membrane reactors were trying to overcome some of the limits of traditional reaction of the kind I was mentioning, and the inorganic membranes at that time were available, and that's why there was an interest. However, the most interesting reactor that we are using today are bioreactors. In case of bioreactor, the term bioreactor means that the reaction we are considering is normally related to biochemicals, and the catalysts are normally enzymes. So there are a lot of limits when you are using bioreactors, starting from the fact, for example, that the enzyme normally can operate at relatively low temperature, 37 degrees centigrade or 50, except you have a specific thermophilic, thermostable protein enzyme. The reaction is at room temperature. And but the kinetic expression and the mechanism of the reaction are different from the one that we are normally using when you characterize water gas shift or steam reforming. Point number one, remember that when you are talking about the bioreactors, and bioreactors are becoming quite interesting and standard for the treatment of these biological, of the municipal water, bioreactors are considered today, membrane bioreactors, are considered best available technology, BAT, in Europe and I think all around the world. In this country, you're in Korea, you have a lot of interest in membrane bioreactors, and they don't tell you, there is no big visibility, but if you go in some of your big hotel and you visit the cellar of your hotel, not too far from downtown Seoul, you in some place you will not find garage or wine cellar, but you will find a lot of membranes, where all the water that you are using at the 20, 15th floor, etc., are continuously retreated and sent again in relatively few hours from the big membrane bioreactors treatment again in the higher flow. That is already happening. That's why we have to learn and to know a little bit about this kind of system, which are quite interesting. The other point of interest is that using membrane reactors, you are solving one of the major problems of the use of biocatalysts. Biocatalysts are normally unstable, and they have a very short lifetime when they are in homogeneous solution, free of any movement. If you want to increase the lifetime, the capability to operate not from a few minutes, a few hours, but to months or a significant number of months at least, you have to go through what's called immobilization. And initially, years ago, the immobilization was done by combining your biocatalyst on pellets, on some powder, or blocking in a column, ion chain column, etc., etc. Today, the best way to immobilize bioenzymes is in a membrane system. You can entrap inside, today we are talking about a mixed matrix membrane, etc. The first example, long time back, of mixed matrix membrane were the biocatalytic membranes. Enzyme entrap, protein entrap in polymers. Long time back. That's why that is what you obtain if you just try to minimize the resistance to the mass transfer, because you just block the decrease the permeability a little bit, so you must be doing the right way. You can have significant advantages. Number one, we discussed already at the beginning, that you can recover continuously the catalyst, the enzyme in this case, which is quite expensive. Second, you are increasing significantly the lifetime of this enzyme. The immobilization, what the urease that normally work for a few hours become few months if you immobilize this way. The only trouble that you have to be able to minimize this mass transfer resistance, and because what is happening that the diffusion coefficients of your penetrance of your reactants through a porous membranes are quite different from the diffusivity you have for the same compound when it's free in bulk in solution in homogeneous system. So that's this difference can be significant, and normally is related to the porosity, to the overall porosity of the system, to the tortuosity of the porous structure, and to more in general also to this just the geometry of the system. You can have situation in which there can be just if there is no pore or just very, very narrow pore, the protein are molecular species with high molecular weight. The lowest molecular weight for a protein, if I will remember, is of the order of 16,000, 18,000. For the other one are going to 60,000, 100,000, millions in Dalton. So that we have to take care of these hydrants kind of phenomena, because the real diffusivity is this related to the initial, the bulk diffusivity multiplied for this term, where epsilon is, as I was mentioning, tortuosity, porosity, sorry, tortuosity, and this term omega, as you can see here, is just what is called the stock radius of the reagent, and the average mean radius of the pore. So depending from this radius, you can have a faster or slower mass transfer in the system, and you have just to take care of this. This term here, this effective diffusion coefficients, if you are assuming that is very well dispersed, homogeneously dispersed in flat sheet membranes, and when you know, if you know the thickness, and in steady state, this is the situation that you can assume, in which this diffusion coefficient for the gradient of the concentration across the membranes is given, is RC is the reaction rate, and X is this space coordinate, and this is the relationship you have. Assuming that everything is simple, is a flat sheet, and you know the thickness, etc. However, this tells you something immediately. For example, when you have your mixed matrix, if for any reason your membranes is swelling, and that's normally happen, the thickness of the membrane you can see in the lab when you are doing your experiments can change with time, just when you put in water or you during the reaction itself. And that means that this term here, the reaction rate and the special coordinate, if they are changing with time for any reason, we are changing basically the overall reaction rate in the system due to the change of the properties of the membrane itself. So that's, and this one of the problem that we have to consider, but it's not the only one. If you have this equation I showed you before, if you put the appropriate boundary condition, so you can see that you can indicate, because at x equals 0 that you are in the bulk, at L1 you're just at the interface of your membrane, and or on the bulk, that x equals 0 and c equals C0, where in this case you indicate with 0 is the bulk. Normally 0 is the membrane surface. In this case it's vice versa. You put 0 in the bulk, and the other term it would be at the interface, and you can try to solve this expression we wrote before, and that is the solution, in which you can introduce one-dimensional numbers. You know, chemical engineers are very familiar with trying to make dimensional numbers. In this case, you have the solution of the equation is on this form, which is a first-order irreversible reaction, and you have all the concentration of the reagent along the membranes, and the Thiel modules is nothing, is just this. Really not normal is not the Thiel, but is this what they call normalized Thiel module, and that is just given by this KL, this divided K divided the diffusivity for V and so S, where S, M and VM are surface and volume of the matrix of the porous membranes. And basically you have also to define in this kind of situation, normally you will find very often this effectiveness factor, this term here, that is the observed reaction rate, what you really measure, you follow your reaction, and you are measuring this observed reaction rate divided by the reaction rate that will be observed in absence of any mass transfer resistance. The problem is that when you immobilize your catalyst in your membranes, the situation is changing. The situation can change during the reaction for many reasons. So this term of the efficiency is what the good researcher is trying to increase and to minimize as much as possible this term of the different phenomena which can reduce this term here. The effectiveness factor is nothing more than what you really measure compared to the situation in which there is basically no mass transfer resistance related to the immobilization of your catalyst. And that is the kind of situation that normally you can define, and depending from the value of TIL of this TIL module, you can have different level of effectiveness. For example, you have this for phi higher than 3, you just assume that the efficiency is quite significant, is approaching 1/phi. But that is just in the experimental results will give you. Typical behavior is here. You can have the effectiveness of fraction. You can see in terms of the normalized TIL number, and that is you can have 1 basically for very low. You have a high effectiveness only for normalized TIL number relatively low. Otherwise, you can have very, very low efficiency. That means what is prevalent is this mass, the resistance that the system is offering you. In many of these membrane reactors, the problem that we have, and that is true particularly when we are talking about also these bioreactors, we want to know the difference between external and internal diffusion resistance, because we can have some limitation, some deviation from ideal behaviors from external diffusion. That means if you just build up gel layer, concentration polarization phenomena, that means in the boundary layers of the liquid film adjacent to the membrane, and from, on the opposite, internal diffusion problem, where the catalyst is immobilized. So we have to take care of two things when we just study this kind of reactors, reaction in this kind of reactors. One is to have a situation in which the immobilization of the catalyst inside the morphology of our membranes is not creating any trouble to the in terms of mass transfer. The permeability is not to decrease too much. It's impossible to avoid 100%, but the possibility to reduce and to have not too much resistance is possible. But when you do this, you are controlling the internal diffusion resistance. But we have also the external one, that's the one that we are been defining as concentration polarization phenomena, the effect at the interface. And so we have normally the flux of our, when you are talking about bioreactors, and we will use this, in this case we are looking some effect as bioreaction, instead the term substrate means reactant. Instead of talking about the reactants, you talk about substrate. So that's exactly the same term that you call reactants. In this case, you can see here that this flux of the substrate is proportional to the driving force. In this case, the difference between the concentration in the bulk and the one at the interface, basically. K is mass transfer coefficient, and CS the substrate concentration, reactant concentration to the bulk and to the interface. In steady state, this mass transfer has to be counterbalanced, as we saw already before, by the consumption that across our membranes. If we are assuming, for example, that you have your reaction is a first order irreversible reaction, you can have this kind of relationship. And in this, also in this case, there is another number that people are, chemical engineers particularly, are using frequently, which is what is called a Damkoler number, which, as you can see here, is the ratio of the mass transfer coefficient. That's quite useful and interesting to utilize. This, because if you know this Dampler number, you can have information about the situation, how much you are approaching the ideal behavior or vice versa. The till number we have been defining before, in which we have been defining the effectiveness factor, approach 1, and we can have a situation in which we have a kinetic control or diffusive control, and that's how this. Depending if you have a kinetic control, the relationship will be between the velocity and concentration will be in this form, and vice versa. In diffusive control, the equation is changing, and that is will be this Ks instead of K, and that's initially concentration. That's exactly what we are talking about. You can have, in a general case, we will have a concentration. This kind of the concentration profile of your substrate of the species converted can be of this form. However, this one can be, you can have this kind of situation where it's kinetic control, there is basically flat concentration profile, and also, or this extreme other case where you have diffusive control. Here we are creating concentration polarization basically, and not here. And that is one of the two situations that we have to consider carefully. And okay, and there are different kinds of obviously of the till numbers in both cases. You can rewrite them in the form that is necessary. I was showing you that one of the most interesting case, we will see some situation related to the bio reactors. When we are talking, we will discuss about the membrane bioreactors, and there will be the equation that we have to use are the same that we have been discussing now. But the case that we are discussing first is the case of hydrogen that we have been already showing before. And the case of hydrogen is the one I was telling you. Hydrogen does not exist pure in nature. So we have to produce hydrogen. And normally one of the way, very well accepted, to produce hydrogen is through steam reforming of methane. So you have to produce methane, simple gas, and you can supply this simple gas to membrane reactors of the one of the situation we showed before. This one is the one in which we have the catalyst compartmentalized outside between the vessel and the inside the palladium tube, and on one side you produce hydrogen, on the other one you produce a concentrated stream of CO2 basically. So that is the kind of situation that we have, and this is the one that people are assuming will operate in the automobile, for example. The automobile with engine, electrical engine will be just have in the back or on the platform, they will have one of these membrane reactors just doing this kind of work, which is not a single step. There will be the fuel cell will be the hydrogen produced, will be the one that will be utilized in the fuel cell for having your engine moving. Keep in mind that some other application already exists of this kind. These are real plants already installed basically in Japan. That is a system that is already producing 20 normal, I don't remember which number here, cubic meter per hour of hydrogen, and that is typical membrane reformer with pure for just used for hydrogen production. I think it's Japanese engineering, this one. Oh, that is a typical one. That's the one in a gas station. That's the one for filling your car, your automobile, for hydrogen before instead of diesel or other form. And that's the one that probably will be the most effective in perspective. And the turbine and the hydrocracking and other application, fuel cell is the future. Now, the production of hydrogen is normally coming from steam reforming of light hydrocarbons, or just methane, or partial oxidation, or cold gasification. Now, if you check the three systems, compared to cold gasification, the amount of CO2 you are producing is terrible, is huge. And this system here, if you realize the appropriate way, is the most interesting. Something similar is a partial oxidation of light hydrocarbons. That's why people are looking into this kind of reaction. And the possibility to use membrane reactors is quite interesting, because in principle you are decreasing the cost of the catalyst, also because in a membrane reactor you can reuse it. You are reducing significantly the reaction volume, and we will see some data, and the kinetics is improving as we predicted in some of the equations we saw before, and we can have also higher conversion. So in principle, the membrane reactors, if this reaction is going to be important, will be quite interesting. That's just propaganda for process intensification, because if it works, you can have all these kind of benefits. In traditional system, you have the problem of still of the CO, the purity, etc. With process intensification and with membrane system that are quite related, we can just have interesting conversion index. You can have recovery index increasing, etc., etc. So that is one of the reasons, and the water gas shift is the most interesting one. This is a complete water gas shift that people are using already in not only for fuel cell, by the way, but in different industrial process for cleaning and for having at the end hydrogen very well purified. So normally here is the reforming, can be steam reforming, and the steam reforming, as I was mentioning before, after the reaction with methane and water, which is basically here, you can just go in the water gas shift, and the CO is going to be converted, and here you have a last step will be the final purification with palladium membranes, and you go in the fuel cell. So that is the water gas shift, as you can see here, is a fundamental step in the upgrading of the quality of your hydrogen, and that is the reaction we are considering. That is a reaction that is thermodynamically favored by low temperature, and in principle, as we mentioned before, does not depend from reaction pressure. However, if you are working with the membrane system, we learn that basically also the pressure can have a positive effect here. That is the situation that you have in a fuel cell, what is quite in the most, or indeed just in the membrane reactors. The CO and H2O basically, they are just converted in the catalyst bed, and the retentate is basically CO, CO2, hydrogen, etc. And you have a if these are the appropriate membranes, enriched pure hydrogen is what is coming across your system. Basically, this is at the moment one of the most interesting systems for what you can have here. First of all, in one unit, both phenomena, that means reaction and separation, high recovery factor, much better conversion compared to the traditional system, as we have discussed before. Interesting here, remember that you cannot, we have been talking always with palladium, but this can be done with palladium alloy membranes for the separation of the hydrogen, but also with silica membranes. And that is totally different. This palladium has infinite iron selectivity. In here you can have a partial selectivity. This is finite iron selectivity, low packing density, high mechanical resistance. Here there's a little bit difference for particularly mechanical properties. And if you want now to check with some numbers, and that's what today engineers are supposed to do, and the effect here is that the conversion is function of feed pressure, as we have been discussing before. If you compare with traditional system, there is interesting benefits. The recovery index is one of the parameters that you can introduce to check the results in terms of process intensification, and that can be done in terms for the silica membranes reactors or the palladium one, and in both cases there is a quite interesting conversion factor, which has a function, as you can remember, we discussed before, of the feed pressure. you are not supposed to increase as function of feed pressure, but in the real life, you can, using a membrane reactor, there is a significant increasing when you just go from 400 kilopascal at one to much higher value. And again here, that is the interesting system for when you go to the fuel cell. The partial pressure is on the plotted function of the length. That's another parameter you have to measure carefully, because today you can realize that depending from the configuration of your reactors, you have to be sure how long will be your system, because a part of the reactors does not work, because the driving force can be just negligible and there is no production of your hydrogen. That's why we, for example, have redesigned a system in which we decide how to combine a system in which we don't lose surface of membranes without any permeation. This is this case, you know, the traditional reactors is this down here, and that is the concentration profile. When you have this with membrane reactors, this is typical behavior. On the other side, you are increasing with CO2, and you can produce about a retentate of about 80% of CO2, basically, which is already concentrated, also compressed. So you can, in principle, continuously reuse if you know what to do with this one. But as I told you, you can react with again and transform this CO2 in many other compounds if you want to do with through the what is called C1 chemistry. What is coming out here is just pure hydrogen as a concentration which are lower than the one normally poisoning your catalyst. And that is the membrane, basically the conversion, which is 5 times higher than the traditional one. If you just look along the length of your reactors, the traditional reactors, the performance in terms of CO conversion in water gas shift is down here. The one we have experimentally at a different pressure are the one up here, which is a 5 times factor of 5, not 5%, factor of 5 higher than international reactors. And all this happened because traditional conversion, we are producing hydrogen, and the hydrogen is still sitting in the reaction volume, so minimizing the blocking the conversion. If you remove continuously, this kind of phenomena you can obtain, which is the one that we were looking for. We were mentioning before the Dampken number. Eventually you want to remember, and that is just giving you this characteristic space-time with characteristic reaction time. And that is one of the parameters that is quite interesting in defining the performance at the end of this membrane reactor compared to the traditional one. But this is in this case you can just replot in terms just of the Dampken number, and you can see here again that the traditional one with Dampken 0, 1, and here when you go to 0, 5, or 1, etc., the one that characterize also the membrane reactors is much more interesting than the other one. And that is the situation. We can have overall a reaction volume reduction of order of magnitude, basically. Normally in a membrane reactor you have this gas, basically 4000 H-1 is the one characterizing this membrane reactor compared to the traditional GSFV in a traditional one. And that's just the condition that are just more favorable that you can obtain. Recovery index for hydrogen is also interesting. Again, 0, 5, 1 in dimensional length, and you can see here for different Dampken number what is happening in a membrane reactor. You can have pure hydrogen with 80 or 90%. Basically, no way you can produce pure hydrogen, and the same CO conversion is arriving to 90% against 15% with the traditional one. That is the case of the traditional, the volume that you can have, the volume index. You can have a membrane reactor volume index compared to the traditional one, and you can see here that is 50%, 30% basically reduction in the volume system. And the function, as we discussed before, of the feed pressure, this 95% that is going to have about 20% of the volume at the end. So you can have quite interesting reduction of the volume index, which means much more compact units and the footprint, etc., etc. Same is here as function of the temperature, you can see quite significant decrease. Other parameters that are all consistent with this process intensification is the conversion index, so conversion in membrane reactor to the conversion in traditional one for a specific reaction volume, and you can just make the comparison, and you can have quite interesting conversion index as function of the pressure, which, as you will remember, is there is no effect at all if you are working with traditional reactor. The pressure has no effect in reaction with no change of the number of the mole. Here are some overall system, the one that people are working today. This is a part of a big project sponsored by the European Union in Europe, in which you can see what people have been doing. That is the core of the reaction was this one basically, but upgrading of the stream coming by a reformer, the one I showed you before. So you're starting here, you have a traditional cleaning of your gas, you remove H2S and poisoning species, but you enter immediately in the water gas shift, and you go to the hydrogen separation, and the objective is just production of pure hydrogen. And that is something that now is becoming, approaching industrial development, is no more at lab scale. And again, here we can summarize some other results, but they are already, you can find in the literature a lot of this data now, and well, that we saw already basically, these 3-4 times higher conversion. There is a problem that I will we were not mentioned before, and we can just remember. We discussed already when discussing general gases for concentration polarization. The problem of CO, remember, is not only a question of efficiency in terms of interfacial phenomena controlling the concentration in the interface, but there is a problem of inhibitors. And some chemicals, as CO, can not only minimize the transmembrane flux in terms of changing driving force, but what can happen is that you can have also a change in the available surface for the absorption, what we called before dissociative absorption of hydrogen at the interface. And that's something that is quite important. Let's see if we can so quickly this mechanism of the phenomena. Everything is coming out except what I was looking for. Anyway, I was trying to show you that what you have to calculate, this is what is called here inhibition coefficients. That means when you are really working in real life, the hydrogen permeance can change with the increasing of the partial pressure of the CO. And this is not concentration polarization. It's something different. The hydrogen permeance can approach what we call here plateau when the membrane surface is saturated by CO. Saturated does not mean that we are only increasing concentration. It means that the CO chemically can be absorbed on the palladium surface and can minimize the possibility of the hydrogen to be absorbed, is a competitive effect, and splitted from a molecules of 2 atoms in a single molecules. So it's a kind of real inhibition phenomena that reduce the active size on which this, assuming that the validity of the model, but the model is the one most interesting today, and it's a kind that you can see a Langmuir absorption law, that we have the CO that is arriving, is blocking some of the active sites where the hydrogen was supposed to interact and to be splitted, and that is and changing the capability of the hydrogen to interact and penetrate and diffuse as native hydrogen. And that's at the end of all this equation. What is here that the hydrogen flux has to be corrected by the traditional sievert flux that we have been discussing before, which is not anymore the one that we were expecting. That's why you realize that something's happening, because there is a strong term here that is just decreasing the available surface where the hydrogen can be splitted, dissociated. So that's an important phenomena that takes place in this case, and this was relatively, if you see here also the reference, relatively new, because it was not known before. And for doing this, you have to study all these hydrogen permeance as function of the different driving force, etc., and make comparison between situation when you assume ideal sievert permeance and the one that is no more ideal, and you can understand what is going on. And today this work has been recently done, and we can just, if the model has been validated, basically, it's telling you that we have to consider this kind of situation also in gas separation system, which is not marginal, because this effect, this parameter here is affecting not 0, 1, but 10, 15, 20% the overall permeance of hydrogen, these inhibition coefficients, which is not just concentration polarization. Basically, this phenomena can be also a function of the temperature. So you can just replot, and you can see here that increasing the temperature, basically, the hydrogen permeance can increase just because you just have less inhibition by CO. So at increasing temperature, this absorption phenomena can be minimized, and that's why you have a quite interesting improvement in the situation. Okay, and okay, I think now we can just stop here, but just tell you that this is, you see, there is a lot of interest in this kind of system, and people are working, and I'd just like to show you this last slide, because that is one of our work. You can see here that these are traditional reactors, and all the inside, there is all these tube is a membrane, is palladium. If you study carefully this phenomena, this inhibition, and the effect of the parameter I was describing before, at the end you can arrive to the conclusion that what can be done is to realize a different kind of reactor in which initially there is no separation. That, you see here we put our reactors in palladium system at a certain length of the tube. Initially there was not, because it was not working. The first part of the system, basically the driving force was not sufficient to make any hydrogen purification, basically, and separation across. So you can save money just starting at a certain level with the recovery of the hydrogen and from the steam reforming reaction that is taking place here. And this is something that is coming out from this kind of analysis, and this is not yet an industrial reaction, but it exists. And that's why you can redesign and you can compare these innovative reactors with the traditional one in terms of this kind of effect. And when you can just measure the hydrogen recovery, you can see that all the data are quite consistent with the prediction. You can find, if you are for any reason interested, this is you can find in literature most part of the results. And what is more interesting are the results that consistent with the process intensification as here. So the traditional reactor should be number 1, and is and you can assume putting a number as this 100. 40%, 65% is just the volume of the reactor, considering the reduction in permeance, or basically not considering the reaction in permeance, which are the effects that are related to this CO or not CO absorption. And that's something that also now is becoming quite common, and to realize what has to be done. Okay, I think we can stop here, and we will continue and meet tomorrow morning. Okay, trying to arrive at the end of this part. Any question? Any problem? No one is working on palladium here? Do you have any interest in palladium membranes? No? Only polymers. Anyway, these are interesting, but also because if you understand what is going on with these membranes, you can understand and predict and design also other kind of membranes. Palladium is natural products, but this behavior is quite interesting. And today there are people trying to simulate on the computer how to reproduce the phenomena that palladium is showing. And that can be quite interesting because nature is never doing something with no motivation. Must be some good reason that was not for our reactors or for some other reason. But what can be done with the palladium can be done in other way. Okay? We'll meet tomorrow morning. Thank you.